Hi, everyone. I'd like to introduce Christopher Vogt. He started working on the Scala programming language and has transitioned into Haskell for the past several years, and has a position at Symbiont. He's going to walk us through some live coding around writing 2D games using some really cool Haskell. Take it away, Chris.
Thanks, Kurt. Thanks, everyone, for joining. So, yeah, I want to share with you something I've been working on the side in the last few months, just for fun. Basically seeing, well, how far can I get trying some game development with Haskell and trying to keep the main code as pure as possible without going overboard. And well, this is what I came up with. So we'll first look at the code of one of the game demos that I have. And afterwards, we'll go through the little engine I wrote to power this game. And I have a mechanism set up that will basically allow us to change the game while it is running. And maybe we get time to look into this later or in the Q&A session. But basically, you see three windows. There's a game window on the top right. There's like some runtime information on the top left, like the frame rate. And the code is on the bottom here. And yeah, so if there's any clarification questions on what I'm explaining, just ask right away and just write it in the Twitch chat, and Kurt will interrupt me. If there's any kind of questions that go a little further, then let's keep them for the Q&A session later. So this is the code for this demo game, and let's first look at basically the data types involved here and the game logic just for this game. So the bunch of textures here, so the spaceship, as we can see on the screen, there will be hearts that we're shooting with and enemies. And just to show the live thing, so let's change the size of the spaceship. So we're recompiling. First time is slow, afterwards is fast. There we go. Okay, let's change it back. So we can basically edit in real time and then see what's going on. Okay, so this game, well, has a bunch of textures, and then it keeps track of well, the game state. It's like the game board, right? So it keeps track of a player position, and the player position is a tuple of doubles. It keeps track of where the stars are in the background. It has...
Hey, Chris, yeah? The sound has gotten a little bit crispy. Is there any tweaks you can make?
Yes, I can try to turn this down a little bit. Let's see if this is better. It's a little, is it still crispy?
Yes.
Okay, let me change here. Okay, how is it now?
Keep talking.
Okay. Let's see. So, yeah, our game, this is the state our game keeps track of: player, stars, hearts, and enemies. And it was initialized at the beginning. There's this function which sets up the game state in the beginning, which put the player at a position 100 and sets up a bunch of stars using random positions within the screen dimensions. And we'll now be going ahead and changing the game a little bit. So the way this all works is there's this function step game state pure, which is called whenever there's a keyboard event, like a keyboard press, or when the engine wants to render a frame. And it takes a bunch of things. Most importantly, it takes the game state and an event, and it produces a new game state. So let's say it notices you press the space key, and then it does something, right? And I'm using this kind of syntax here to import all the fields of the game state and all the fields of the engine state, which is another thing the engine keeps track of, just into our scope here. So let's do something very simple. The render event is the one that is emitted every time a frame needs to be rendered. And let's just basically look at what happens here. So when a render event comes will produce a new game state. And in this case, we'll just take the existing game state and we don't do anything interesting. We keep the player the same, we keep the stars the same. So when a render event happens, so when a frame needs to be rendered, we change the game state, right? So let's do some simple stuff to the game state. Let's say we'll change the player position by increasing the X position of the player. And I implemented a num instance for tuples, so you can just plus basically the player position with this. So we see now the plane is moving forward, right? So that's the basic technique how we can move an object on the screen. At -1, we'll move it backwards, or -10 will be very fast. Okay, let's, whoops, okay, stop this right there. But instead, what we want to do is we want to move it with keyboard events, right? So now I'm pressing some buttons. You can see it up here, but it doesn't do anything. So let's get the help of these little functions, move player X, move player Y, which modify the player position. So they take the old position and then they check, hey, if the key W is a member of the set ES keys pressed, and that's one of the fields made available by the engine, then we'll take the old position and we'll subtract something. What we subtract is the tuple 0, 200, but multiplied by ES time passed. Remember those old games where you got a faster processor and the game would run faster? Yeah, we don't want that. So we don't want the game speed basically to be dependent on like the rendering speed or any other speed. So we basically normalize it by the time. Dupe just takes this value and makes a tuple because this is a tuple and we can minus another tuple, which we multiplied with this tuple. So here we can basically do simple vector arithmetic just by using tuples. We do the same for S. So now that we have these functions applied here, if I press W and S, we can just move the plane, right? And now the same for move player X. We have A and D. We can move the plane sideways. Okay, so that's nice. That's one thing. Another thing I wanted to do is I wanted to have the stars in the background fly sideways. So we can basically, so it looks like in a way the plane is flying forward. And again, we want to modify the X position. So X is the first component of this tuple. Let's see. So this didn't work because, oh, stars is a list. So we can't just subtract this tuple from a list. So what we need to do is we need to turn this into a function, and we need to do this for every element. I'm using the basically postfix map, fmap operator here for that. And this doesn't work because of Haskell's special handling of minus, so we need to use the subtract function in Haskell. See, now you see the stars moving. The only problem is the stars are leaving the screen. And it makes sense, they move into the minus, but we really want to kind of have them stay on screen, right? So that's a bit unfortunate, but what we can simply do, we use the modulo function to get them back within the range of the screen positions. And since we have tuples here, not individual values, I wrote an additional modulo function that allows us to do this component-wise on tuples. So mod2 does it basically on a 2-element tuple. And the dimensions here are just provided by the engine. So now, whenever a star leaves the screen on the left, it comes back on the right, and now it gives the illusion that there's a background running. Okay. So another thing we might want is enemies to shoot at. And so we have this GS hearts and GS enemy fields. And let's see where they come from. So enemies, the enemies are whatever, the new enemies are whatever the enemies were before, excluding the enemies that were hit, but plus the added enemies, which is an empty list, and the hit enemies is an empty list as well. So it's really just the old enemies that were there before. And we didn't have any right now, so there's none there, right? But we would like 10 enemies, and we would like to add whatever basically fewer than 10 that we have. So we're going to add 10 enemies. And the way we do this is we just produce the screen positions for them. And screen positions are tuples, right? So we'll just use zip to produce a list of tuples for the screen positions. We say repeat 900 in order to just put them all at 900 so we can see them. Ideally would be a little bit outside of the screen, of course. The resolution is 1024 by 768. And then for the Y positions, we'll just produce a bunch of random doubles at natural numbers. And we produce whatever many we need within our window size. And SND takes the second element of the window size tuple, which is the Y position. So let's do that. So there we have a bunch of enemies. Okay, so we probably want to make them fly as well, right? So again, let's basically subtract something for each enemy in this list. So we'll make them move. Now the only thing is, okay, now they left the screen, and we can see here in the debugging information, oh, they're somewhere in a minus, which is also not great. For enemies, it's probably not a good idea if they just flip over, right? If they kind of come back to the same position they left, it's a bit weird. So we want to just remove the ones that have left the screen and produce new ones. I mean, we already have the logic to produce new ones up here, right? So we just need to remove the ones we don't like. So we'll just go ahead and we'll filter. We filter all of these enemies, and we say, hey, we want to only keep the ones where the X position, which is the first entry in the tuple, is greater than 0. And then they get removed and new ones appear. And what's the problem here? Oh, I forgot the dot to combine these two functions in the filter condition. Okay, beautiful. So now we have enemies that just fly out of the screen, and whenever they're gone, they will come back. Let's put them a little bit further out so we don't really see them randomly appearing. Okay, so now they will fly in. And they will always be at different positions, won't they be? Yes. I mean, they overlap a little bit, so that's something we could fix later. But okay, so now we want to shoot at them. And I already have some logic in here that says if we press the space key, we're adding to the list of hearts because we're shooting with hearts. And what we do is every time we press space, here you see these little things appearing here, we'll basically add these things, but we add the player position. So basically relative to the player position, we add them at different places. And obviously I took the coordinates for these little points here. So we know how to like put them in places, but they don't fly yet. Okay, so let's make them fly. Let's make them fly. So let's just be quick and I'll copy this logic here. So again, for each element in the list, we'll add a speed on the X coordinate, but we make it relative to time, so it doesn't depend on the frame rate. There is a typo here. Accident, okay. Okay, now they're flying away. They have the same problem like the enemies before where they're just flying outside of the screen. So let's put a filter here as well, which just says, okay, if they left the screen, we'll just make sure they disappear. So we don't like have infinitely many hearts. But now they don't like hit the enemies yet, right? So we want to basically implement collision detection. Okay, so we have this hit enemies, hit hearts, which are already kind of removed from the ones. We just need to fill it with something that makes them, make us list here the enemies that actually have hit. And what we can do is, well, we have the enemies variable, and we have the hearts, and we can use the applicative operation here to basically create the Cartesian product of those two. So every enemy combined with every heart. And then I'm going to write a helper function, collision may, which will basically give me a like a maybe, so adjust for of the pair when they were hitting each other. So we check every enemy with every bullet if they were colliding, right? And if they did, then we return adjust. And if they didn't, we'll return nothing. And then we have a list of maybes. So let's throw away the nothings, cut maybes, which will give us a list of the collisions, and unzip it so we can have like 2 separate lists here. And that's the logic we need. But then we still need to figure out if they're colliding, right? So let's write that. Collision may. For every enemy and every heart, we need to check if. So we have the position of the enemy, but we don't have the dimensions yet, right? Like the enemy texture has a certain size. So there's this helper function tdim, which basically just gives us, for the texture ID of an enemy, it gives us the dimensions, which we need here. And then we put it in a tuple with the enemy position, and that's what the collision detection helper function that my engine provides basically needs. And then the helper function is called collides with. And so we check if at this position with these dimensions, we have a collision with the bullets, which are the heart positions with the heart dimensions, right? And then if they were colliding, we'll just return them, and else we will not return them. So now I'll put this together. We should have a list of the hearts that collided with enemies, and we should have a list of the enemies that collided with hearts, and we remove them. So basically, this should give us the effect of being able to shoot things. Let's see. Yep. You see the enemies, the little bullets disappear, the little hearts disappear as well, right? Okay, so we got ourselves a little game. So let's see what the engine actually does to make it happen, right? So let's get this full. Okay, so step game state pure is going to be called every time an event happens or when a frame needs to be rendered. But it only returns a game state, right? We still need to kind of go from there to actual rendering on the screen. So there's another function, visualize, and both of those will be called by the engine. We'll see where at the right times. Visualize takes a game state, and it's called also when a frame needs to be rendered, and it will produce a list of sprites. Sprites are basically positions with textures where to put them on the screen. So there's this helper function as well, which says, oh, for a texture ID, so in this case, the spaceship, and a position, so GS player is our player position, we'll produce a sprite, which is really just binding the texture to this position. We'll just produce a list of these things. And really, this is what you do, what you have to provide for a game, and then that's what the engine works with. So let's go quickly to the main module of our game to see how basically we wire up these functions with the engine.
Hey, Chris, one quick question that's been coming up is, sure. What is the recompiling framework? What are you using to have it automatically?
Yeah, let's take that question for later.
Sure. Okay.
But it's basically just GHC, or it's a GHC interpreter. The same thing powering GHCI and GHCID. Okay, so the main function of the game called playtime. Playtime is my code name for my little engine. And this is just mostly code hooking up this live reloading feature. But the most important thing here is make engine config, which is this function. Again, ignore the live code stuff. But it produces an engine config, which is really the information given to playtime to tell it, okay, how do you progress the game state? How do you visualize things? So it uses this helper function, wire engine config. And the first two arguments are the most important ones, step game state and visualize. Visualize we already saw. Step game state is down here, which is a little bit of IO surrounding our pure step game state pure function we looked at earlier, right? So it produces a random IO, like one integer, which is used as a seed for the deterministic random number generator inside of the pure function. And then after it produced a new game state, there's another check where like I can reset. Okay, but basically what it does is, this is a function that does a little bit of IO, but returns a new game state. So we give this little function doing I/O and this one doing, I think, no I/O to wire engine config. And let's look inside of wire engine config. This is really what makes the communication between different threads happen, because the way it works when you, so I'm using this GLFW library, and you get the key presses and the mouse events and all this stuff on different threads than the main thread where openGL is running. So somehow you need to get the information from the one thread to other threads. And well, one way to do this in Haskell is mvar, so mutable shared thread safe variables. And basically, I'm storing the game state in an mvar, which is set up by this wiring function. And then I'm producing basically a new function EC step game state, which is part of the engine config, which calls our step game state, but it gives us the old game state that comes out of the mvar, produces a new game state, stores it back in the mvar. So this is how basically stepping game state updates the game state all the time. And for visualize, we also have this EC visualize around our pure visualize, which just here reads the game state. Ignore the texture stuff. I won't go into it for now. Okay, so this is kind of the setup we give to playtime. It already knows how to basically pass the information between the pure game step function and the visualization function. So let's look at this function playtime. And really, the most important thing it gets here is an engine config. You can ignore the live code and the mvar thing, but basically you give playtime the engine config and it takes a bunch of stuff out. Most importantly, the EC step game state, which we defined earlier, which updates the mvar, and EC visualize, which uses the mvar to produce the list of sprites. So, and what playtime does, it with GLFW, it produces an openGL window. Then it sets up callbacks for the keyboard events or the mouse events, and it passes this step states function to the callbacks. What step state does, it's similar to the updating the game state mvar. The engine also maintains an engine state mvar. But really what happens inside of step states is, oh, take the old engine state, blah, 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 step the engine state to the next one. Then we step the game state using this function we defined earlier, then return the new engine state. And it is called in two places. It is called whenever a keyboard event happens, but it's also called in a loop periodically, which is basically the rendering loop, right? So let's quickly take a look at the keyboard hookup. So basically set event callbacks gets the step states, and this is functions from the GLFW bindings that allow us to say, oh, when there's a mouse button, then call the callback that steps the game state basically for this event, happens in that thread, and so on for the other things. This is basically how, how the events are applied to the game state. And then in the main loop, while M, so basically until we decided to quit the game, it will every time, basically every loop iteration here renders one frame. And it's actually openGL that by default limits this to 60 frames using the vsync that maps it to the refresh rate of the monitor. So we step the states, which steps the engine state and the game state, take the new engine state, we pass it to EC visualize, which knows how to read the new game state through the mvar, produces a list of sprites, and then we pass this to renderGL, which is part of the engine here, which takes a list of sprites and does all the openGL stuff, right? It like, you see openGL is a fairly imperative API, right? Oh, we want to use a blend function. Okay. Next, we define the blend function. Okay. And then what really happens here, for each of the sprites, which are all of this rectangle type, all have an area and all have a TPE, which can be either a rectangular fill type or a GL object, which just refers to a texture. So if it's this, which we used for the stars, we'll just draw a little square using render primitive, which is an openGL thing. Primitive is like any kind of sprite or something. Figures out the corners, and then for textures, it will draw a texture and It's how we talk to OpenGL and how we limit it. I think one thing I skipped over earlier that I want to go into. So back to the game logic, we use this helper collides with, right? Which is really what checks the overlap of two things, so collision detection. So let's take a quick look at this. There's a fairly simple kind of way to do collision detection, which is easy to find on the internet as well. So basically, you take the dimensions and the coordinates like of the left upper corner and the dimensions and the coordinates of the other one. And then there's like a formula how you compare, oh, x greater the other x and y greater the other y and stuff like this. So it's a very simple function. Yeah, and I think we're out of time. So I think we'll move over to the Q&A room. I'm happy to do a bit more changes on the game or to show, I have a little jump and run prototype and a kind of a top-down placing tiles for walls and walking kind of through a maze kind of demo as well. All right, thank you very much for your attention. I'm handing back to Kurt.